So now we go to the Landau theory, which I will spend about, I think, some 15-20 minutes on that. So Landau theory is this saying that although it's largely phenomenological, but it's the beginning of the conceptual framework of understanding phase transition. Okay, so read this, but also let me, in the meantime, also let me briefly tell you. So 1937, when Landau did the theory of phase transition, it is a general theory of phase transition, and it paves the way for everything that followed. It is a very simple theory, incredibly simple theory, and but however, this generality that it allowed and the new concepts that brought in, which was not there before. And one of the new concept that Landau brings in, he asked the questions that I was asking here. How do I take the characteristics here in the old phase, which I know contain the key for the phase transition? So how do I do that? What are the way I go about incorporating this? So he rightly now guessed that the way to do that I need to have the, so I have the minima. I have the minima in the liquid, and I have all the correlations here. So now if I can expand the free energy of this phase in terms of free energy of all the characteristics of this phase, then I can look for a certain discontinuity. So that is of course ambitious, and it is the reason it does not fully work, but that is the one it is called the, so this is again my favorite line. Some of the predictions are not quantitatively correct, but the main merit and the strength of Landau theory is its tremendous generality that comes with a simplicity that is unmatched in theoretical discussions, and you will see that. But the reason I am preparing you for that, though it is a very simple theory, it opened the door for many theories, and it is the generality that is absolutely mind-boggling. So what it did? After saying all these things, what Landau did, okay, let me write down the free energy of the new phase. Free energy F is the new free energy of the new phase in terms of a simply called Landau expansion in a Taylor series. In a Taylor series of, see, people were all very perplexed for many years, decades. Nobody wrote down such a simple expansion, but Landau wrote down. That is what actually probably the simplicity or whatever is the genius. So he expands. So this is the, when you expand like that, then eta is the order parameter. So I am expanding free energy in the order parameter. In the old phase, order parameter is 0. So F equal to F naught. Now my aim is to find a solution of the free energy in terms when the eta is non-zero. Okay. So this is the search of a solution. What are the conditions? Then where then the answer lies? The answer lies, as I said, answer lies in this branch. Answer lies in this branch. And where are these branches are going to? All these quantities, alpha, A, B, C, all of them are temperature dependent. This is explicitly put out for reasons I will describe a little later. All of them are temperature dependent. Now, what are these quantities? How do I get alpha, A, B, C? Exactly. You take the derivatives. So that's the characteristics I was saying. We need the derivatives. And once you try to find the derivatives, you go a little deeper, you find the derivatives are in fact not only just specific heat or compressibility, but they are also given in a little higher level theory, intermolecular correlations in the old phase, which we are not going to go. So this is the famous Landau expansion. There are many other terms there. This when you put the gradients here, delta eta term, that becomes the Ginzburg-Landau, and that is the one of theory of superconductivity people use, or superfluidity. Ginzburg, who got the Nobel Prize later for this and many other things. So now we start playing some games. So these are first important things, they are determined by derivatives of the free energy in the old phase. So these are determined by the old phase, and we are trying to by Taylor expansion, just like we do. How do we do a Taylor expansion? We always do Taylor expansion by going from known to unknown. That's the Taylor expansion, right? Interpolation, extrapolation. So Taylor expansion always like we do f x plus a, we do a Taylor expansion f x plus then first derivative, but evaluate it at x a. So whole idea is that of going from known to unknown, and known we know, we are entitled to know everything about the old phase, and then we are trying to do new. Now first thing is that because this is a free energy minima, because this is a minima here in the liquid phase, this is 0. So now it becomes simpler, that the free energy is one term less. Next, very importantly, one quantity is done. Now I make a distinction between first and second order phase transition, and this is a very important. So I will now describe something else that is coming here, but coming at a later stage, so I better do it here. This is extremely important thing and essence, important part of the Landau theory. Okay. So in a first order phase transition, free energy surface behaves like that. This against order parameter, free energy, and I am lowering temperature towards the transition. So this is the old my parent phase, this is the daughter phase, parent, daughter. Now parent and daughter become stable. Now what is in my pressure density, what is this point? Exactly, this is the coexistence point. So this is a metastable. Characteristics of first order phase transition, that there is always a metastable phase. One of the major characteristics, and what is the manifestation of the metastability? We see it all the time. What is the most important manifestation or a signature of metastability? Hysteresis. You see in the presence of magnetic field, huge hysteresis. That is because system remains trapped. Even when this is stable, system is trapped here. That is one of the reason. Another reason, even at coexistence, there is a large barrier in first order phase transition. What is the consequence of this large barrier in a first order phase transition, gas to liquid, liquid to solid, or nanomaterials, whatever? Nucleation. You cannot spontaneously go over from one phase to other phase, because it is a macroscopic barrier which is proportional to number of particles in the system. So it must be, new phase must be nucleated. Okay. So two important characteristics of first order phase transition is A, metastability, hysteresis, B, it must be nucleation. Because there is a macroscopic barrier, so a system must be, it's like a winning a war, you must get into the fort. Okay. This is a first order phase transition. What is happens, so this is the Landau free energy surface for first order phase transition. What happened to Landau free energy surface for second order phase transition? Like the order disorder transition, like superfluidity. Now, this is very nice and very nice. This is what is the Landau theory gives you a nice physical picture. This is low temperature. Now I am increasing temperature, or you can say decrease temperature, whatever. you will see so uniquely different. With this is the time I really miss a big board. This T equal to Tc, this T say less than Tc, T near Tc, and then T greater than Tc. Let me see T greater than Tc, T greater than equal to Tc, and T less than Tc. So, there are the 4 diagrams. So, there is no metastability in a second order phase transition, there is no nucleation. So, as I go to the transition point, the systems, remember I told in the response function, second derivative are the springs that hold the system together. Here this spring is compressibility or susceptibility or the specific heat, and that spring slowly goes away. That is why you have infinitely compressible at critical point, and the free energy surface becomes really broad and shallow in the minima, and this is where things are diverging. And just below, little below that, you get the spontaneous symmetry breaking of the system. So, this is Landau provides this free energy landscape. The free energy provided this beautiful picture how a first order phase transition happens and a second order phase transition happens. This is how first order, what is shown here is first order, what I have drawn there is first order, and there is a huge change in going from melting is a case where there is no second order phase transition, and there is a beautiful logic, again Landau logic, that in a gas liquid, however, there is a second order phase transition. This becomes narrow, you remember the isotherm, then this is the critical point, inflection point, this is Tc. And so, as you approach that, then free energy surface become, even in the minima, become flatter, and then the whole second minima completely disappears, and you get the so this is the one that is shown there is the first order phase transition with metastability, and then I will do the Landau theory in a minute, and this is the flat, and then this is the spontaneous symmetry breaking in a second order phase transition. Okay. So, let us do the Landau theory quickly, and so knowing that free energy surfaces are very different, Landau trivially now included this. He said, okay, first thing I again mentioned that is an order parameter, that is why order parameters was introduced, so that I can expand the free energy. Order parameter is the change, and you know the free energy expansion is done in Taylor expansion about a change. So, in Fx plus A, our Taylor expansion A is the order parameter. You are expanding around that, and so order parameter is the smallness parameter. Okay, that is number 1. Second, now we going to do the second order phase. If we do first order phase transition, then this quantity B is non-zero, and if B is non-zero, I can make B negative, and by making B negative I describe this transition, and that is exactly the way Landau-Dijan theory of liquid crystal was done. Dijan was given Nobel Prize for 2 work, one is liquid crystal, another is polymer, or 3 are semiconductor also. In these 2, liquid crystal and that, he did the Landau theory. So, is it beautifully one can describe, and it turns out I can do the calculations of B, and in first order phase transition they are negative. What is an example? Let us do the van der Waals gas. I am taking again and again. So this is the van der Waals gas, our famous van der Waals. And then this is the free energy. For integrating this one, you get the free energy, and I can plot the landscape, free energy landscape from van der Waals. I can also do expand free energy in a Taylor expansion. Van der Waals gives you exactly this, what we discussed the other day, virials. These are my virial series. Beauty is that the second coefficient is this thing. Now, free energy is derivative, go over, you get a term, cubic term, you integrate that, get the free energy. This term becomes negative at a low temperature, simulating the phase transition, first order phase transition. And this goes to, the cubic term goes to, becomes small near the gas liquid critical point. That does not fully describe this theory, but Landau theory is essentially van der Waals theory. These are called mean field theory, in the sense that I am neglecting fluctuations. I am using a simply Taylor expansion to describe the, if I integrate that, rho square, rho cube, that comes in. So van der Waals free energy is exactly Landau free energy, except I now have some little bit of ideas where R, B and B2, B3 are done. Okay, it already has them. Now, the strength of Landau theory is in providing a description of the second order in a trivial way. Now, second order phase transition here, there is a symmetry. The symmetry is that free energy is invariant. If it is 0, this plus, this minus is the same. This is called the degeneracy. So, if it is so, then this free energy, the condition, so often called the parity, symmetry condition, and then this becomes simple like that. This is very famous, you know, particle physics 5-4 theory, many theories, you know, K.G. Wilson himself did it. It has a huge impact on the enormous field of field theory. This Landau thing, that means it went in so many different directions. Whole polymer is, I told you, liquid crystal, everything is done in this language. This is more, I like to tell that this actually gives you the language of the phase transition. That teaches you how to think about phase transition, how to think of free energy change, okay, and order parameter. So this is now simplifies, and now Landau made this brilliant thing. He said, okay, A is a strongly temperature dependence. I assume A, T, this is not the Helmholtz free energy, it is constant A, and this is a universal language of Landau theory. This kind of expansion is the absolutely standard. Now you get, so I make this. Why do I do that? I did it because when T goes to Tc, so this is this term, then this term is the one that is the spring, that's the frequency, right? And told you that this is a response function, this we know will be specific heat, actually 1 over specific heat, but so this thing is going to be flat. So that's why he assumes that it goes to 0 as a T minus Tc, and then I solve for eta with that condition, put this here, now I go and find out this, take a derivative. When I take the derivative, I get eta equal to 0, always remain a trivial solution, because this phase always remains a trivial solution. This is minimum here, but in maximum the same condition also holds, and then I solve that, I get, this is the, so the order parameter, this is a remarkable prediction, that order parameter has this non-classical dependence. That means even when, look at this beautiful thing, if Tc minus Tc is 0.1, I go below 0.1, I am in this regime, I am gone below the critical temperature. What is square root of 0.1? 0.33, right? I go to 0.01. What is square root of 0.01? 0.1. What does it mean? this kind of fractional exponent means he is a huge dependence. And this is the real hallmark of critical phenomena, these fractional exponents. This exponent is called alpha, is a specific heat. No, sorry, this is called beta because it is in terms of order parameter, and beta is universally 0.3 or 1 by 1/3 close to. This is amazing. You do so many different systems, define the order parameter and consider the temperature dependent order parameter, and you find the fractional exponent almost always 0.33. That is why it captured the absolute A of imagination of scientists across the discipline. This universality is a characteristic of critical phenomena, and these are called critical exponents. Yes. No, what you have actually, you have absolute value here, and there are lot of these exponent beta, above and lower called beta and beta prime, and there have been lot of work on that, and beta prime are almost always the same. They might be slightly difficult, but very difficult to do the experiments exactly very close to that. But experiments were known for a very long time. This is exactly exponent you find from van der Waals theory also. These are called the Landau theory does not get correct exponent 1/3, but it captures one of the essence that so eta is the change. So eta will be, if I go below this, I come from here to here, then this will be the order parameter. So what I am saying is that by giving change a small amount, the eta is going to change by a big amount. Okay, that is a singularity that we talk about in order parameter. Okay, so there are all these different kind of order disorder transition. Isotropic nematic is very closely second order, and then gas liquid is a thing. So going back to first order phase transition now, like liquid crystals, or van der Waals describes the first order fairly well, that then B is non-zero anymore. It is the B that changes the sign. Now, what Dijan did in liquid crystal transition in isotropic nematic, he noticed that the isotropic nematic is nearly second order, though first order. So he kept Landau theory. He kept Landau this part, and then he also kept the B term, and it developed a theory. Again, same spirit, same phenomenology, nothing great, but he also again captured the, described the liquid isotropic nematic phase transition in liquid crystals, which is given here. I think this is what I wanted to tell, the Landau theory and the free energy landscape of Landau theory, then the critical exponents. So there are some other critical exponents which one should not, I don't like to say that, but the other critical exponents are the following: specific heat, alpha, eta, just a minute, I might be making something wrong. This is beta, and specific heat alpha, I should have had that. Then order parameter is a beta, and there is gamma, delta, a series of critical exponents which compressibility, yeah, compressibility goes as gamma, specific alpha. Alpha is typically 0.1, beta is typically 0.32, gamma is typically 1.8. Landau theory predict this is half, Landau theory finite discontinuity here, and this one Landau theory predict 1. So Landau theory gets is the value is wrong, but it does get the basic physics correct. So, should I write it separately, these Cp, Cv, or you can see these things, Cp, eta and chi, and these are the exponents, critical exponents, alpha, beta, gamma, and as I said, they are universal. That means they are nearly the same across all the systems. This is a good question. Van der Waals is a mean field, Ramakrishnan-Yusuf is a mean field, Landau is a mean field, all are the same at the end of the day. The reason is that when I expand that, these are the ones with guys working on phase transition, right, day in and day out. Okay. Now, in all these things, now let us consider gas liquid, simple thing. In a gas liquid near the critical point, what happens? There are regions which are liquid like, there are regions next to it which are gas like, large scale density fluctuations. You look at the density, and now I look at the density as a fluctuations around the average density. In my critical Rostar language, critical density is again universal in near 0.3. It's very interesting, near 0.3. I take that out and look at fluctuations. Then what do I see? I see there is a region like here where is my origin. I draw like that. There is a large value. Then after that it becomes negative. Then become large, then becomes negative. I find out that. So delta rho, this is liquid, this is gas, this is liquid, like that. Need not be periodic, there is not periodic, but there are, so what are these now? These are interfaces. What does interface bring in? Bring in surface tension. It an extra energy. Where is that in Landau theory? It is not. So Landau theory has to be supplemented by and lo and behold, you have one of the most powerful theory of the world, this Ginzburg-Landau. So Landau, Van der Waals doesn't have this extra term, which is we call effect of fluctuations. So mean field theory does not have the effect of fluctuations. You have to go to Ginzburg-Landau to do that. That we all do when you do surface tension. In my book, we have dealt with it at length. Surface phenomena, nucleation, these are one of the main the topics in my book which are not dealt in either in physics or in chemistry books. No, you don't have the coexistence. You have, no, you don't have coexistence. You have a point. See, coexistence is a line. So as I drew there, that line coalesces. It becomes a point of singularity. Here, this is where large fluctuations are going on. Gas-like and liquid-like in magnetic phase transitions, you have the up spin and down spins and you know, ordered and disordered. That means one place is ordered followed by a disordered region. So these are the then the order goes away and becomes fully disordered. So the coexistence. So this is a flat free energy interface. There is no. There are inside it gas-like and liquid-like, but those are microscopic or mesoscopic domains. They are essential and ingredient for the fluctuation, large-scale fluctuations. We call the exact language is large-scale fluctuations, but those large-scale fluctuations are affecting the thermodynamic properties, but there is no macroscopic interface. This is a very important question that you asked, that the very essence of a critical phenomena. And so one, I go over, take care of those fluctuations in this term, and then a huge amount of difficulty that comes in cannot be solved, and that's where comes an important way how to go next step. And that was done by, first thing was done by Kadanoff by he said he introduced how the length scale diverges. That's called Kadanoff transformation. There's a beautiful book by Shankang Ma, Dynamical Innovation Group, Dynamics of Critical Phenomena. He described it beautifully and there's a wonderful review article for high school students essentially, but first year PhD students called Mattis and Kadanoff, Physics Today, 1979 or 78. Wonderful. That's the best of critical phenomena that I know of. Kadanoff and Mattis or Kadanoff. Both were at Brown and they wrote together, and we got the preprint. Everything was done in one dimension, which is done, that particular article almost in toto in my book, the critical phenomena. So, doing that was done step by step. Kadanoff did the Kadanoff transformation, says how to treat the emerging correlations, long length correlations that happens, things become correlated over long, so because the fluctuations become correlated, that because here if I have a liquid like regime, then I has to have a gas like regime. This is called fluctuations getting correlated. Then one of the most powerful theory of modern times, K.G. Wilson in 1970 or 71, did the innovation group, which is a lot of fun to that. I did that once. I was very lucky in Chicago to work with one guy called Yoshi Ono. We did the innovation group calculations of polymers, but it's an amazing theory. Okay.